So today's lesson 3.2 is on exponential growth and decay. So we previously had our lesson 3.1 on linear functions, and the characteristic of linear functions is they have a constant rate of change represented by a constant number as the rate of change. Today it's going to be a constant percentage rate of change. So just to draw the distinction between where we were and where we're going today. So let's just get right to it. Just using this example to kind of get you a taste of how exponential growth works in a real life scenario. We have this bacteria that reproduce by division. And we start off with 2,000 bacteria in a dish, and we're told that the population doubles every hour. So the 2,000, of course, that we start with is the initial value, and then we're going to determine what is the percentage rate of growth from that number, and in this case that's the 2,000. So just doing some simple math. If we're told that the population doubles every hour, then after 1 hour we would expect 2 times the initial population, or 4,000. And then after the next hour, then that number would double, so 4,000 becomes 8,000. And then we don't have it on the screen here, but after the third hour, 8,000 becomes 16,000. So in general, we just take the population at the end of the previous hour, and the next hour would be that number multiplied by 2. That's pretty basic. So the percentage change, just to show you how exponential functions represent a percentage change in the data over the course of the entire data set. So using our first example, the percentage change over the first hour, well, we ended with 4,000. We began with 2,000. So I'm just doing a review of how we find the percentage change in data. So we find the difference between the 2 hours divided by the original, which we started with 2,000. So this is 2,000 over 2,000, which is, of course, 1 times 100%, and that represents a 100% increase. And then we could do the same thing over the second hour just to make sure we're consistent. It should be a constant percentage. So over the second hour, we ended with 8,000, began with 4,000, and then divided by the number we began with. Well, that's 4,000 over 4,000 again, which is 1 times 100%. So just proving that we do have a constant percentage rate of change. And doubling, like we are here, always corresponds to a 100% increase. I think we just proved that. The population grows not by a constant number, that would be a linear function, but by a constant percentage. And in particular, in this case, that would be 100%. Growth by a constant percentage characterizes exponential growth. So in this example, the population size is called an exponential function. So size, population size, is an exponential function of time. Okay, another example. This time we're told that the population triples each hour. Okay, so we start, let's just pick a number to start with, just to illustrate properties of exponential functions. We started, let's say, with 100 in a population. After 1 hour, if it's tripling, that becomes 300. After 2 hours, 300 will become 900, multiplying by 3. So again, analyzing the percentage growth rate, after the first hour, we do the ending amount minus the starting amount, 200. and that's 200% increase. And then the same thing happens over the second hour. You can see the math, because if you divide by the original here, you get 2 times 100%. Here, if you divide by the original, you get 2 times 100%. So multiplying by 3, or using the word tripling, results in a 200% increase. And since the population is growing at a constant percentage rate, the population is considered to be an exponential function of time. We'll do one more of these. What about quadrupling? Well, the same thing. Does this represent constant percentage growth? The answer would be yes. And you can probably pick up on a pattern. If doubling represents 100% percentage growth, tripling represents 200%, then quadrupling, which is 4 times, would be 300%. So the answer to yes, this does represent constant percentage growth. The percentage is 300%. Is the population size an exponential function of time? Well, yes, because we do have a constant percentage growth. We have constant percentage growth. Okay, so moving on, now that we understand a little bit about how exponential functions work, let's talk about the equation forms that they take on, or sometimes known as formulas. So in general terms, this is what exponential functions look like in equation form. So y would be the ending value. A, as you can see here, just trying to drill down on this, A would be considered the initial value. So how much did you start with? And then y would be how much did you end with after you multiplied by either a growth factor or a decay factor. Okay, so this base, B, stands for the base of the exponent. If it's exponential growth, we'll come up with that base by doing this little simple calculation. We'll have to be told how much the rate of growth is in percentage form, and then we do 1 plus that percentage as a decimal, and that will be our base for the exponent. And then the exponent here represented as x, here it's represented as t, because typically that will be some sort of time unit. The rate of growth will always be given in terms of a certain amount of time, whether that's months, years, days, hours. So the difference between these two, of course, one is growth, and our B, our base, is obtained by doing 1 plus the rate of growth. And if it's decay, it's all the same, except a big difference here. We're going to do 1 minus the rate of growth, the percentage. Okay, and here's some more just to remind you of what was just said. Make sure you take the percentage rate of growth or decay as a decimal, and then do the addition or the subtraction depending on whether you have growth or decay. All right, so here's another example. The value of a certain investment grows according to the following rule. Next year's balance will be found by taking the current balance and multiplying by 1.07. All right, so our base, in other words, is 1.07. So that means the rate, find the percentage increase each year. The actual percentage increase, percentage rate of growth, is the 0.07, which would be 7%. Why is the balance an exponential function of time? Because this is a constant percentage rate of growth, just the definition of exponential functions. Namely, it's growing by 7%. Each year in this case. Okay, assume that the original investment is $800. Find an exponential formula that gives the balance in terms of time. Okay, so you could use whatever variable you want. If you want to say B equals the balance equals the initial investment amount, and then the base of the exponent again will be 1.07, 7%. And then t, the exponent for this base, will be how much time has passed. So that would be, letter B would be the function that would give us the balance after any number of years. Okay, well then the next question is, well, what about 10 years? So then we'll get specific and we'll take our formula and we'll replace t with 10 and get the actual amount. All right, so you just grab your calculator and 800 multiplied by 1.07 and then raise that to the 10th power. And we'll round these to the nearest penny. That's 1,573 and 72 cents. All right. Next example, it's very similar. Looking at this rule, the percentage increase would be the 3%. If an initial investment of $450 is made, let's write a formula. So our ending balance will be taking the initial balance, multiplying by 1.03 raised to the number of years power. Okay, oh, I'm sorry, this is months, so you got to be careful. We're told that this is the percentage increase each month. That's what T represents. All right, and so what is the balance after 2 years? Well, T is in terms of months because that's the way the rule specifies. So we're going to have to change years into a number of months. So you really have to be careful there that you use the correct time unit. So 2 years would be 24 months. All right, so 450, 1.03 raised to the 24th power. And in terms of dollars and cents, that would be $914.76. All right, this is just an example of how rapid exponential growth happens. It starts off maybe relatively nominal, nothing out of the ordinary as it begins, but over time we'll see in this example how it really increases rapidly. So what this wants us to do is find the growth in the balance in terms of dollars over the first 10 years. Okay, so let's see how much it grew. I'll just call this in 10 years, how much did this investment become? And I think we already came up with that number in a previous problem. We did the same, it was the same rule. How much did it become after 10 years? And that's the 1573.72. So that's how much the investment was at the end of 10 years, but how much did it grow? So to see how much it grew, we would just need to subtract off the original amount. And then that represents how much in terms of dollars that the investment grew to become. All right, so we'll just grab our calculator, 1573.72 minus 800. So it grew by $773.72 in 10 years. All right, now let's take a look at, we got letter A. All right, now let's compare in letter B that number compared to the growth between years 40 and 50. All right, so let's do the growth for 40 years. So we're just going to put 40 in for T. Let's see what that is. 800, 1.07 raised to the 40th power. and that is 11,979.57. But let's subtract off the original, the 800, and running out of room here. To get the growth amount, so that's 11,179.57. Okay, so in terms of dollars, that's how much it grew in 40 years. Now let's do the 50-year growth. So we'll take that same formula, let t become 50, and you should get 23,565.62, and then to tell how much it grew in terms of dollars, we'll subtract off how much we started with, and that leaves us with 22,765. Okay, so in terms of dollar growth from year 40 to year 50, let's see what that difference is. So if you subtract these two, you're going to get an overall growth in this 10-year period of 11,586.05. All right, so our comparison is this was 10-year growth. This was total dollar growth over the years from 40 to 50, a 10-year span. Well, you can see, let's see how many times greater this number is versus the first 10 years. So we'll just do some division. So 11,586.05 divided by 773.72. So it's about 15% times greater. So this number is almost 15 times greater than the 10-year growth. Again, just to give you an example of how fast, that's rapidity, how fast the longer something goes, in the later years it's really starting to pick up a lot of movement. It takes off very rapidly. So we'll do the same thing here, this next example. In 20 months, let's see what the growth of this investment would be at the end of 20 months. So T is going to be 20 in this case. So we got 106,132, and then subtract off the initial to get how much it grew in dollars. So that's 661.32. Okay, compare that to the growth between months 50 and 70. So if you plug in 50 for T into the same formula, at the end of 50 years, the value of the investment is 4586.96. But subtracting off the initial 400 will tell us how much it grew. So it grew by 4,186.96. And then month 70, same thing, we're going to let T become 70. The balance of the investment at the end of the 70th month is 12,170.57. Take off the initial 400 so we can see growth, 11,770.54. Okay, so the comparison is the growth in the investment after 20 months versus the growth between months 50 and 70. So when we subtract these two numbers to get the overall growth in this 20-month time period, we get 75.83.61. That's the difference between these two. Okay, and so now I'm comparing final number that represents the growth between 50 and 70 months versus the growth in the first 20 months. This number is about 11.5 times. the earlier growth. And if you're wondering how I got the 11.5, you just take 758361 and divide it by the 20-month number, 661. Okay, let's move on to another example. We have a certain job opportunity that offers a salary of $50,000, and we're told that we're going to get a 5% salary raise each year. So in looking at this opportunity, we want to know how much our salary would be in 15 years. Okay, so we can call this S for salary. We start with the initial value. Remember, in general, it's y equals ab to the x power. A is the initial value. B is either a growth factor or a decay factor. In this case, it's going to be a growth factor because we're getting a raise. So we're changing 5% into a decimal, and then we're going to add that to 1. So that becomes 1.05 is our base. And x is the number of years that have elapsed. So to get our answer, we just let x become 15, and we will be done. So 50,000, 1.05 raised to the 15th power. And we have 103,946 and 41 cents. Okay, we have healthcare expenditures in 2010. We're told that they reached almost $2.5 trillion. There's a prediction out there that states that going forward from 2010, expenditures will grow by 6.5% each year. Assuming this growth rate continues, let's get a formula that gives healthcare expenditures as a function of time. So I'll just say H for healthcare expenditures, starting with 2.47 and then growing from there by 6.5%. So 6.5% as a decimal is 0.065. And then we're told that this is a yearly growth rate, so T is going to be expressed in years. So to get my answer for the second part, what will the expenditures be in 2030? Well, that's a 20-year period. So I'm just going to take my formula that we came up with above and let T become 20. And when you plug that into your calculator, you're going to get 8.7. And don't forget, this is expressed in trillions of dollars. $8.7 trillion can be expected in 20 years from 2010. Okay, decay works very similarly. We talked about this earlier, except to get B, we're going to start with 1 and then subtract a percentage rate of decay. So we have a bacteria population that is dying off. Okay, that's what decay means due to contamination. We started off with 2,000 and the population is declining by 75%. So I'll just say P is population, initial value of 2,000. So this time we're going to do 1 minus 0.25, that's 25% as a decimal, and that's 75%. And this is an hourly rate of decay, so T in this case will represent a number of hours. And so letter B, I can use that formula and predict after 7 hours. So I just take my calculator and I plug in 2,000 times 0.75 raised to the 7th. And you should get about, since it's living things, we'll round to the nearest whole, should be about 267 bacteria remaining after 7 hours. Okay, one popular example of exponential decay is half-life, and this occurs a lot with radioactive material. So let's take a look at some specific examples. The half-life of a radioactive substance is the time it takes for half of the substance to decay. So the thing here is very similar to what we talked about with exponential decay in our previous example. It's just that for half-life problems, the base is always going to be 1/2 or 0.5. And H is going to be the time in half-lives. So we'll have to do a little calculation. It always represents the time in half-lives that we're expected or asked to determine. So let's just do one example of these. We have this radioactive substance that has a half-life of 450 years. We have 20 grams initially. So let's come up with a formula. We'll just say Y is how much of the substance remains. If we started with 20, the base for these half-life problems is always going to be 0.5. And then I'm going to let H represent, as it says, the number of half-lives that remain. Okay, now let's use this to specifically answer this question. How much is going to remain after 720 years? So we need to convert 720 years into half-lives using the information that we were given in the problem. So in terms of half-lives, we would do 720 years divided by 450 years, which is 1 half-life. And when we do this calculation, we get 1.6. So that's going to be my H. So you will always be taking the question in terms of typically years, but we got to convert into half-lives. So you'll take the number in the question, and then you'll divide by this given number that's provided in the narrative in the paragraph. All right, so to get our answer, we're going to raise 0.5 to the 1.6 power. And that's going to give us about, rounded, 6.6 grams of this substance would remain after 720 years if it had a 450-year half-life. All right, so that takes care of the examples, the notes. Hopefully this will prepare you now for doing the practice problems that have been assigned. Please let me know if you have any questions, and I will see you at our next meeting.